This is Chemistry Podcast 9.5, and we're going to talk about the pH scale and then how you can calculate the pH and hydrogen ion concentration and hydroxide ion concentration. So what we're trying to figure out is why are some solutions acidic, others basic, and still others neutral? We did talk about this a little bit in the podcast 9.4 because we said that acids were something that contained hydrogen ions. They produced hydrogen ions when we put them into solution. Hydroxide ions were from bases. So we know that when we put some of these solutes or these acids and bases into solution, they produce hydrogen ions and hydroxide ions. And those are the two things that determine whether a solution is going to be acidic, basic, or neutral. So I want you to pause the podcast and copy this down, fill in your notes so that it looks like this, and then you can follow along with what we talk about. What we have here is the hydrogen ion is shown in red, and then the hydroxide ion is shown in blue. And it's really important to note these square brackets right here. They have a purpose. The square brackets are telling you concentration. You read that as concentration. So square brackets, they mean concentration. And remember, concentration is another word for molarity. So what they're saying here is that as the concentration of the hydrogen ion decreases, it gets less, the hydroxide ion concentration is getting more. There is always some hydrogen ion and some hydroxide ion in a solution. It's the ratio, though, that determines whether it's acidic, basic, or neutral. So on this half of our rectangle that we have here, the hydrogen ion, the red, is greater than the hydroxide ion. And we know then, because hydrogen ions are produced from acids, that that must be an acidic solution. So if the hydrogen ion is greater than the hydroxide ion, we have an acidic solution. That's what this is saying over here. If they are exactly the same, which is what is happening right on this black line that runs up the middle of the rectangle, then that tells us that we have a neutral solution because the H plus is equal to the OH minus. And then on the other side of this rectangle, we can see that the blue is more concentrated than the red. There's more blue than there is red. So since there's more hydroxide, this side would be basic. And that would be because the concentration of the hydroxide ions is greater than the concentration of the hydrogen ions. We also can relate this to pH, and pH is something we'll get to a little bit later, but pH is just a scale that scientists use to rank acidity or basicity. The lower your pH, and usually your range is from 0 to 14. So the lower your pH, the closer it is to 0, the more acidic and the more hydrogen ions you have. The higher your pH, the more basic your solution is. And again, we'll talk about this more in a few minutes. Right now, we're going to focus on just the hydrogen ions and the hydroxide ions. So this is just summarizing what we just said. Acidic solutions have more hydrogen ions than hydroxide ions. Basic solutions have more hydroxide ions than hydrogen ions. Water, we're going to stop and talk about for a second because it can act as both an acid and a base. So what water will do is, because it can act as an acid and a base, it often self-ionizes. So if I had pure water, two water molecules can come together. One can act as an acid, one can act as a base, and they'll end up moving a hydrogen from one to the other. We'll end up with hydronium and the hydroxide ion. So water is able to ionize itself. It doesn't do this to a really big extent. There's not a whole lot of these ions floating around, but it does happen a little bit. And sometimes you see a simplified equation where they just show one water molecule breaking up into H plus and OH minus. But you just need to be aware that water can do this, and this is why it's able to act as both an acid and a base depending on what we put it with. Pure water contains equal concentrations of hydrogen ions and hydroxide ions. And from this, we were able to determine that solutions in general have concentrations of hydrogen ions and hydroxide ions. And if we multiply those, we always get 1 times 10 to the negative 14th. So if we think of pure water then must have 1.0 times 10 to the negative 7th molar hydrogen ions and 1.0 times 10 to the negative 7th molar hydroxide ions. That would be for water. Pure water, neutral water, everything's equal. That's what it looks like. This can also hold true though for other solutions. So as the hydrogen ions go up and the solution becomes more acidic, the hydroxide ion concentration is going to drop down. But I will still be able to multiply them together and get 1.0 times 10 to the negative 14th. And that's a nice relationship for me to know, because as long as I know one of the concentrations, either the H plus or the OH minus, I'll be able to figure out what the other one is. So in our first practice problem, it says at 298 Kelvin, the hydrogen ion concentration is 1.0 times 10 to the negative 5th molar. What is the hydroxide ion concentration in the solution? And then is the solution acidic, basic, or neutral? Well, they're giving me the H plus concentration and I'm asked to find the OH. So I'm going to use that formula that we were just talking about. The H plus times the OH minus always gives us 1.0 times 10 to the negative 14th. I know the H plus, they gave it to me in the problem right here. So I'm going to take that and I'm going to plug it in for H plus right here. So 1.0 times 10 to the negative 5th. I multiply that by the hydroxide ion concentration, which I don't know, has to be 1.0 times 10 to the negative 14th. And then to solve for this, I'm going to divide both sides by 1 times 10 to the negative 5th. And once I do that, I end up with 1.0 times 10 to the negative 9th. And because these square brackets mean concentration, which means molarity, I label that with a big M for molar. So if I have 1.0 times 10 to the negative 5th molar for H plus, my hydroxide is 1.0 times 10 to the negative 9th molar. The second part of the question said, is this solution acidic, basic, or neutral? Well, a lot of people look at these two numbers because I have to compare which one is bigger. A lot of people pick this one because 9 is bigger than 5. But you need to remember that we're dealing with negative exponents. So if I were to rewrite these, the hydrogen ion concentration would look like this. 1, 2, 3, 4, 5. That's what it would look like if I were to write it out in decimal form. This one would have 8 zeros before the 1. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1 here. So we can see that the smaller number when we're talking about negative exponents is actually the bigger concentration. That means since H plus is bigger than OH minus, this is going to be an acidic solution. So that answers the second part of our practice problem. Practice problem number 2, I'm just going to do A for you. You can do B and C on your own if you want more practice. H plus right here is 1 times 10 to the negative 13th. I'm going to use that same formula that we were just talking about. So I plug that in for the H plus. It's got to be multiplied by the hydroxide ion concentration, and we have to get 1 times 10 to the negative 14th. When I divide both sides by 1 times 10 to the negative 13th, my hydroxide ion concentration comes out as 1.0 times 10 to the negative 1st molar. So there's your answer. Whoops. There's your answer for this question right here. And then if I look, it says that the H plus is to the negative 13th, the OH is to the negative 1st. The OH is much bigger than the H plus, so this solution is basic. And you can go ahead and practice that with parts B and C using that formula. All right, as you've noticed, the concentration of the hydrogen ions and the concentration of the hydroxide ions are unusually small. They're pretty tiny numbers. We're using negative exponents. So scientists came up with the pH scale, and the pH scale is based on logarithms. And what it does is it takes those really small numbers and it makes them kind of into numbers that are easier to use. So for example, it's usually 0 to 14. We can take those tiny concentrations and they do the negative log of them, and we'll talk about that in just a second. And they end up with the pH scale, which is a much nicer number to deal with than those numbers that are in scientific notation. But if we take a closer look at this, we can see that the acids, so hydrochloric acid, upset stomach acid, normal stomach acid, your vinegar, lemons, sodas, your acids are down here below 7. So below 7, these are all your acids. This is where it would be acidic. Above 7, that's all your basic solutions. So baking soda, milk of magnesia, bleach, sodium hydroxide, antacids. Those are what you take to neutralize the excess acid you have going on in your stomach. So acidic, basic, you can see how they go on here. Another thing you need to know is as we move on our pH scale here, as I jump from 0 to 1 to 2 to 3 and I keep going, each of those jumps is a factor of 10. So depending on how you're moving, you're going to say it a little differently. But for example, if I moved from a pH of 1 to a pH of 2, my acidity went down 10 times. So it's 10 times less acidic if it has a pH of 2 as compared to a pH of 1. If I go from 2 to 3, it's another 10 times less acidic. If I go from 3 to 2, it's 10 times more acidic because remember 0 is the really acidic stuff. If I make 2 jumps, so say I went from a pH of 2 down to a pH of 0, that's a factor of 10. This is a factor of 10. That comes out as 100. So a pH of 0 is 100 times stronger than a pH of 2. And you can kind of get an idea of how those are all related because they're all factors of 10. And we visited this when we started out with that diagram, but we're going to talk about it again right here. If the pH is greater than 7, it's basic. If the pH is less than 7, it's acidic. And if the pH is at 7, then it's neutral. So you can see how this pH scale works. It's really important that you understand the smaller the number, the more acidic you are, the more H plus is in solution. Okay, here's how they calculated pH. pH was calculated by taking the negative log of the H plus concentration. So all you're going to do is you're going to punch in negative log and then you'll type in the hydrogen ion concentration. The number that comes out is the pH, and it should be between the range of 0 and 14. There are exceptions. It can go beyond 14 and below 0, but most often it stays between 0 and 14. The POH is the exact same thing except you use the hydroxide concentration. So POH, you take the negative log of the hydroxide ions, and when you punch that number in, you end up with the POH. The POH is another scale. Oops. Go backwards here. The POH is another scale that's used by scientists sometimes, but the pH is the most common. So that's the one that we're going to focus on, but you still need to be able to do this calculation. It's also important that you know that the pH plus the POH always add up to 14. So if we know one of these, we can figure out the other because they always add up to 14. Okay, practice problem number 3 says, what is the pH and pOH of a solution if the hydrogen ion concentration is 2.5 times 10 to the negative fifth molar? Since I'm given the hydrogen ion concentration, I'm going to be able to find the pH first, because from what we just talked about, the pH is equal to the negative log of the hydrogen ion concentration. So what I'm going to do on my calculator is I'm going to put negative log, and the log should just be a button that says log. On most calculators there is one if you have a scientific calculator. It really depends on your calculator, but most of the time you will go in this order. You'll hit the negative sign, and then you'll push the log button, and then you'll type in 2.5 times 10 to the negative fifth. And if you're struggling with this, come in and see me in class and we can look at your calculator and see what it's saying, and if I can help you out. So with this one, we do that, and when I punch that into my calculator, I end up with 4.60. So this equals 4.60. That's my pH. We just said also that the pH plus the pOH always add up to 14. Well, now I know that the pH is 4.6. My pOH, all I have to do to find it is just subtract 4.6 from 14. So 14 minus 4.6 has to give me my pOH. And when I do that subtraction, we get 9.4. So there's my pOH, here's my pH, and I answered the question that they asked me to there. All right, practice problem number 4 says, household ammonia has a hydroxide ion concentration of 4 times 10 to the negative third. Calculate the pH and the pOH of this typical cleaner. So in this problem, I'm given the hydroxide ion concentration first. That means I'm going to calculate pOH first, because the OH is directly related to the pOH. I'm going to do the negative log of the hydroxide ion concentration, which would be the negative log of 4 times 10 to the negative third. When I put that into the calculator, I get 2.40. So there's my pOH. To find the pH, I take 14 and I subtract 2.40, just like we did, but we're kind of going backwards because we found the pOH first and now the pH, and we get 11.6. So there's your pOH and there's your pH. You need to be pretty comfortable going from the hydroxide or the hydrogen ion concentration to the pH and the pOH. Those are pretty important calculation. The last thing here is, because I'm able to go, what we just did there, I'm able to go from the concentration of hydrogen ions and hydroxide ions to the pH. I can also go backwards. I can go from the pH or the pOH back to the concentration of the hydrogen ions. So I can solve for this. And to do that, I do the inverse log. And the inverse log is just 10 to the negative pH. So you can either, a lot of people do second and then the log button, or maybe it's shift and the log button. But if you find your log button on your calculator, usually right above it, it says 10 to the x. That's what you use when you're trying to do this, when you're trying to go back to the hydrogen ion concentration. You can also just punch in 10 and you can raise it to the negative pH, whatever that is, and you can do it that way. So you don't have to do the second and the log. You can just type in 10 and raise it to the power of the negative pH. And I'll show you how all this works on this table right here. I'll do a couple of these with you, and then the rest of them you can try them on your own and come ask me if you have questions. So on this first row, we're going to work our way through it. I need to use everything that we've talked about. So flipping back through all of your notes that we just did, all of your formulas, I know that the pH plus the pOH always add up to 14. So if I take 14 and I subtract 2.3, I end up with 11.7. And that's how I'm going to solve for the POH and the POH, or the pH and the POH. They always have to add up to 14. So these add up to 14, those two right there. Then to go back to the concentration, that's what we just talked about, doing the inverse log. I know the pH, but I don't know what the hydrogen ion concentration was. So what you do is you put in 10 to the negative 2.3. I raised it to the power of negative 2.3, which is the pH. And when I do that, I end up with 0.005. That is the hydrogen ion concentration in this solution. I do the same thing with the hydroxide ions. I'm going to take 10 raised to the negative 11.7 this time. And when we do that, we end up with a much smaller number, but it's 2.0 times 10 to the negative 12th. So the pH and the H plus are directly related, and then the POH and the hydroxide ions are directly related. So you need to make sure that you're using the correct, maybe pH if you're going to H plus and POH if you're going to OH minus. Then we have to answer the question, is it acidic or basic? Well, the hydrogen ion concentration is way bigger than the hydroxide ion concentration, plus the pH is less than 7. Both of those things tell me that this is an acidic solution. So I'm done with the first row. The second row, the POH is 4.5. So in order for me to find the pH, I have to subtract from 14. So 14 take away 4.5 is 9.5. And that's how I can find out both those numbers. Then to work backwards again and find their concentrations, I'm going to use that inverse log, the 10 to the negative pH and then the 10 to the negative POH. So 10 to the negative 9.5 gives me 3.2 times 10 to the negative 10th. There's that one right there. Then to find the hydroxide ion concentration, I take 10 to the negative 4.5. And when I do that, I get 3.2 times 10 to the negative 5th. So there's both my concentrations. In this one, the hydroxide ion concentration is larger and the pH is above 7. So both of those things tell me that this is a basic solution. So see if you can work your way through the rest of this table. Come in and ask questions if you're still stuck or if you're having problems figuring out how to use your calculator with these, and I can help you out. And that is it for podcast 9.5. So remember, you don't have to memorize the different formulas that we just went over. Those are things that'll be given to you. The big thing is that you can pick out the correct formula to solve for what you need. So understanding the relationship between pH, POH, and then the concentration of the hydrogen ions and the hydroxide ions, those are the really important things from this podcast.